All right, so yesterday we talked a little bit about equilibria with acids and bases. I know a lot of people are a little rusty, so just to rehash what we covered yesterday. We said in an acid-base reaction, we'll have some sort of acid. The acid is going to be the proton donor or receiver? Donor, right? And then I like to show the base just as generic B. This will be our base. And like we said, the base is going to essentially reach over and grab this proton. And then the covalent electrons, that pair, must be dumped somewhere, and that's going to be on A. So we can show this as an equilibrium reaction where A now has a negative charge, and the proton that was transferred is now on the base, right? And we said that this is the conjugate acid or base, the A, with the negative charge. The base. So this would be conjugate base. Like I said, this is the thing we really care about. And then over here, we have the conjugate acid. All right. Now I'm going to kind of spin this on its head a little. If we think about the solution at equilibrium, are all four species present or only two? All four. At equilibrium, these are all present in solution, which gets confusing, right? Because then we could say, well, we've got two acids present at equilibrium. So let's make a note of that. So two competing acids are present. All right, so now the question is, how can we tell which side of the equilibrium is favored? How do we know if the equilibrium is favoring the left side or the right side? Anybody have an idea? Yeah, whichever acid is stronger is going to essentially win out, right? So we have to have some inherent understanding of the stronger of the two acids. The way I like to describe this is the stronger acid will push the equilibrium. All right, so let's take a look at a few examples, because right now we're just talking A's and B's. We can't really tell which one's stronger here. All right, so the first one we'll look at will be a relatively easy one. We'll do hydrochloric acid, so HCl, and water. We know just by the name that hydrochloric acid must be the acid. So I'll just go ahead and label that as the acid. And we know that it's going to give up its proton, just like we saw above, to our base, which in this case is going to be water. Then we're going to dump electrons onto chlorine. That gives us a chloride anion with a negative charge. Let me clean this up a little. And then the hydronium ion as well. So if we think about the conjugate acid, it must be the hydronium ion. This gets confusing for people though. They're like, well, in Gen Chem I was taught that HCl is a strong acid, but I was also told that the hydronium ion was also a strong acid. So how do I know which one's stronger? If you're ever in doubt, the best thing you can do is find experimental data, right? You can't argue with experimental data. So how do we measure the strength of an acid? PKA. All right, so what we'd do is we'd go to a table and we'd say, all right, I want to find the PKA of HCl. And the most common PKA table that organic chemists refer to looks kind of like this. This is called the Evans PKA table from Dave Evans at Harvard. There's some in your textbook as well, but arguably his is the most exhaustive list. And we would try to find the closest possible match. So if I go and I look here, I would look through the table and I'd say, all right, HCl looks like they've got negative 8.0, and then in parentheses it says 1.8. What do you think the parentheses mean? Not quite. If we look up here, It's a little bit confusing. It says DMSO on one side and then water over here. Was this reaction done in water or something called DMSO? It looks like up here we were in water, right? So we would want to go to this. Occasionally, you'll see DMSO. DMSO is a unique organic solvent. Sometimes we have acids that don't dissolve readily in water, so we have to go to an exotic solvent. So in this case, the value we want to look at is the negative 8.0. So I'll go ahead and plug that in. Say, all right, the value here is going to be negative 8.0. That's pretty good, right? We know strong acids have really low pKa's. All right, then we'll go over here and say, all right, what's the pKa of this conjugate acid? Well, we'll go back to our table and we'll say, all right, we've got H3O plus. Aha, it must be negative 1.7. All right, so we'll go ahead and plug that back in. All right, so now the question again is, which of these acids is more acidic, HCl or hydronium? HCl, it's more negative, right? Meaning a smaller or lower value. So that means that this must be more acidic due to the lower pKa. So if we think about the equilibrium position, is it going to favor the right-hand side or the left-hand side? The right-hand side. So what I often do is I'll take out these equilibrium arrows because that's kind of unclear, and I'll say it's going to really, really push there. We're going to get a little bit of pushback to the other side, but really the right-hand side of the equilibrium is going to be favored at equilibrium. Does that make sense? So we're going to have a much, much higher concentration of chloride and hydronium ion at equilibrium than water and HCl. Does that make more sense? So these tables, students oftentimes look at these and they're like, this looks like a lot to memorize. You do not need to memorize these values. Please don't. It's a waste of time. There are a handful of values that you can memorize from your book that are useful benchmark values, but you can use these tables to find the closest match. There are a handful of values that I think are very, very important. The first one is water. So we can always compare things to water and say, is it more acidic than water or less acidic than water? That's, I think, a pretty good benchmark value. pK of about 15.7 is a good one to remember. The rest of them I'll typically give you on exams or quizzes. Sound good? All right. So now we can predict equilibrium positions, but let's say we don't have a pKa table and we just have to go on our gut instincts. Then we need to predict relative acidity all on our own without a table. So let's make some notes. Whoop, that's not what I want. And like I said, this is what happens when you don't have a pKa table. All right, just like before, we would say, I've got my acid, I've got my base. This is going to be in equilibrium with my conjugate base and my conjugate acid. This is our general equilibrium that we look at. Just like you saw in your pod, the thing I really like students to look at is the stability of the conjugate base. All right, and there's a lot of different features that can stabilize that negative charge. What's one we can think of? Resonance, we saw that on our problem of the day. What's another one that could stabilize a negative charge? So you're talking about orbitals. Orbital size definitely can change that as well. What's another one we talked about a lot in general chemistry? Electronegativity is a huge one, right? So oxygen is going to be a lot more happy with the negative charge than carbon, for example. So there's a lot of different features. All right, so let's come up with a list of features. So various features can stabilize a conjugate base. And I've got a good acronym for us to remember. All right, the acronym is cardio. I guess it's cardo with the I offset. It's okay though, we'll figure it out. All right, so the first thing we've got is we've got charge. So is a conjugate base going to be happier with or without a charge? Without a charge. We know neutral compounds are a lot more stable than charged compounds. So that makes a lot of sense. That's very important. So this is most important. And then as we go down the list, we'll get to less important. All right, A has to do with atom. Like we said, electronegativity is the direct result of the atom carrying the charge. What do you think R stands for? Resonance. So resonance is actually less important than the atom, surprisingly. Next one is called dipole induction. We'll talk more about what that means. And then last is orbital. So this is a pretty good priority list. First thing we look at is charge, then we look at atom, then we look at resonance, then we look at dipole induction, and last but not least, we look at orbitals. This is a good general guideline. There will be situations where there are outliers that don't fit these trends. However, my goal is never to trick you. I'll let you know if there's kind of an unusual one. All right, so let's walk through each of these. We'll start out with charge first. And I like looking at each of these with examples. All right, so first one. Makes a lot of sense. Let's say we've got the hydronium ion around a base. We can really quickly say, all right, this base is going to steal this proton. Does it really matter which proton? No. And then give electrons to that oxygen, and I should have shown a positive charge there. All right, if we think about the conjugate base, what would that be? Water. And then we've got our conjugate acid over here, and we'll compare this to water. So water can also act as an acid. So these are two completely separate reactions, right? We're comparing apples and oranges here. But what we really want to do is we want to compare this conjugate base to that conjugate base, and then ask ourselves, which of these is more stable as a conjugate base? The neutral one, right? So this is going to be more stable. Because it has no charge. All right, once we look at that, then we can go back to the original molecule and we can say this must be the stronger acid. I'm sure a lot of you are thinking, yeah, no kidding. But there are a lot of situations where students forget to look at charge. Charge matters a lot. All right, any questions on this? Nope. All right, let's do the next one then. Next one we said was A for atom. And this one actually does get a little bit trickier. So the first thing we're going to look at is electronegativity. That was the one that Susan was talking about. And we will again look at a few different examples. I like doing simple ones. We'll do water with the base versus methane with the base. All right, in each situation, we have a proton that theoretically could be given up. Doesn't really matter which one we show. And we can show the conjugate base. Then down here, same thing, we can show the conjugate base where carbon now has the negative charge. And just like before, we would say, all right, is this conjugate base that I've circled in green more or less stable than the conjugate base I've circled in purple? Which one's more stable? The green one, right? Because oxygen, being an electronegative atom, is okay carrying that negative charge. So again, we can say this is more stable because oxygen is more electronegative than carbon. Again, going back, that means that this must be the stronger acid. We were able to do this without referring to a PKA table. We're just using basic intuition. All right, the next one is a little bit tricky though. We can't always compare things by electronegativity. Sometimes we've got competing trends. Next one is atomic size. Whoops, not atomic side. All right, and I'll kind of show you an example here using hydrochloric acid and a base versus hydroiodic acid and a base. In each situation, we can have an equilibrium where the base is going to grab a proton. So we can show this with reaction arrows. And we can show the conjugate bases. So on top, we would have Cl- as our conjugate base. On the bottom, it would be I-. Oops, this should be HB. And again, we can look at this and we can say, all right, what's more stable? Chloride or iodide as an anion? It's tricky, right? If we think about electronegativity, which one should be more stable? Chloride, right? We would think that iodide being less electronegative should be a lot less stable. The reverse is actually true. Again, this goes back to atomic size. Which one is much bigger? Iodide. So if you think about a negative charge, if you're a negative charge, would you like to be stuck in a little itty bitty electron cloud or a giant electron cloud? A giant one. So in this case, we would look at this and we would say that this is more stable because negative charge is in a large electron cloud. That means that correspondingly, this must be the stronger acid. All right, so now the question is, well, how can we compare these things? It's actually not as tricky as you might think. So if we're looking up at electronegativity, electronegativity is used when we're comparing two atoms in the same horizontal row. So you see how oxygen and carbon were in the exact same row? That's when we compare electronegativity. So I'll say comparing atoms in the same row. So not too bad. We saw that oxygen and carbon are in the same row. If we look at atomic size, chlorine and iodine aren't in the same row, but rather in the same column. So we'd say, all right, this is when we compare atoms in the same column. So then students will always ask me, what happens if they're not in the same row and not in the same column? What do you think the answer is to that? Get a PKA table. It's just easier to look it up at that point. Your intuition will not be very reliable if you're comparing things that are just abstractly different from one another. So this really only works if you're comparing things in the same column or same row. All right, what's after atom? So atom is a combination of electronegativity and atomic size. What comes next? Resonance. All right, so now let's jump into resonance. Let me zoom out a bit. All right, resonance is a lot easier to explain. In fact, you already did on your own with your POD. But let's compare this. What's this molecule called? Ethanol. It's the stuff we're purifying in lab this week. So ethanol we could potentially think of as an acid. It has protons to give away. All right, let's compare this to this molecule underneath. This could also be an acid. Intuitively, you might predict which one's going to be more acidic. The top or bottom? Bottom, why? Because it's named a carboxylic acid, right? It's kind of a giveaway that the bottom one's going to be a lot more acidic. But either way, let's check and confirm this with theory. We could say, all right, in each of these we can give up a proton. And in the top one, we would create an oxygen with a negative charge. That's called an alkoxide anion. And on the bottom, we would still have an oxygen with a negative charge, but this would be called an acetate anion. All right, and so if we go through the cardio rules, first thing we'd look at is charge. There's a tie, right? It's -1, -1. So then we go down the list of priorities and we look at atoms. In this case, negative charge on oxygen versus negative charge on oxygen. We're still tied. Then we go to R, resonance. We know that the bottom one has resonance. And in fact, if you want to draw your resonance structure, definitely practice it. So we can go ahead and dump electrons up to that oxygen. And we can say, all right, the negative charge doesn't belong to one oxygen for the lower conjugate base. It's actually shared between the two. So immediately we can look at this and we can say that this is more stable due to resonance. Remember that this is only a tiebreaker after you've gone through the charge level, after you've gone through the atom level, then you look at resonance. However, it does tell us that this must be the stronger acid. Make sense? All right, so that one's a lot more intuitive. It's something we've been practicing a fair amount. Please keep in mind that if you're struggling with resonance, that means you're likely going to struggle with acid-base chemistry. So make sure you go back and review resonance if you are struggling pushing arrows. All right, next one is dipole induction. Often this is just referred to as induction. Doesn't really matter. I might refer to it either way, either as dipole induction or induction. I like dipole induction because it makes cardio sound better. Otherwise, it's Cardo, which, yeah, doesn't work as well. All right, so we've got this one. Let's take a look at some examples. And again, I'm going to do ethanol with the base versus this competing one. But this is actually going to be fluorinated ethanol. So just like before, we can say, all right, this base can snag this proton. This base can snag that proton. And in the top reaction, looks pretty similar to what we did before. And in the bottom reaction, it still looks pretty similar. However, this bottom one, we have a bunch of fluorines. All right, so now my question is the conjugate base circled in green more stable or less stable than the conjugate base circled in purple? Gets a little bit tricky, right? So if we go through the cardio rules, we look at charge. We've got a -1 tie. Then we go to atom. Looks like it's tied, oxygen and oxygen, right? Then we go to R, resonance. Is there resonance in either of these? No, it's impossible to have resonance in either of these. All right, then we're stuck with dipole induction. Does anybody have a gut feeling for which one they think is more stable? Top or bottom? I see some people pointing down. Why do you think the bottom one might be more stable? Yeah, there's a big dipole due to the fluorines, right? So the fluorines are actually tugging on that, creating a dipole. So you can say there's kind of a tug going this way and that way, which in many ways is going to stabilize the negative charge, right? So the fluorines wanting those electrons is going to hog electron density away from that oxygen, which in this case stabilizes it. So this is where dipole induction comes in. Which means that correspondingly, this must be the stronger acid. Does that make more sense? All right, I've got another one I want you to consider along the same lines. All right, let's consider the following. So both of these have 2 fluorine atoms on them, and they can both react with the base. So I'll just go ahead and show the arrows. You're welcome to include the arrows if you want. I'm just doing it for clarity. Oops. All right, so my question for you is, let's compare the, again, green and purple conjugate bases. Which one's more stable, or are they equally stable? It's confusing, right? So one could argue they both only have 2 fluorines. Wouldn't that make them equally stable? What do you think? So they both have the same number of hydrogens as well. In fact, these are constitutional isomers.
Is it the proximity of the bonds?
So Anthony's bringing up proximity, right? Do dipoles have equal effect regardless of how far away they are? No. In fact, dipoles have a distance correlation associated with them. So knowing that, which one do you think is going to be more stable? The green one, because that has the electronegative atoms closer to the negative charge and therefore will tug on that negative charge a bit more. So we could look at this one and we could say that this is more stable because the fluorines are closer. That means that this must be more acidic. So it is important to remember that dipole induction also includes this distance effect or proximity effect. The closer that negative charge is to electronegative atoms, the happier it's going to be because those electronegative atoms will tug on that electron density. All right, let's do another one. Last but not least, we've got orbitals. All right. We've talked a lot about orbitals, but let's do a comparison between the following. Say we've got methane and a base versus, oops, let me include my carbon there, acetylene. Does anybody know what acetylene is used in on the bottom here? Torches, welding torches, right? So oxyacetylene torches actually use this molecule. Methane on the top is just natural gas, essentially. So in either of these, we can say, all right, we've got protons we could theoretically rip off. Make a conjugate base. Versus this one on the bottom. Again, doesn't matter which proton you choose to abstract or deprotonate. It gets a little bit tricky. So again, we are comparing conjugate bases. Whoops, let me make this purple. If we go through the cardio rules, we've got a -1 tie at the charge level. Then we go to atom. It's a carbon-carbon tie. Then we go to resonance. Can't do resonance with either of these without forming a Texas carbon of some sort. So that doesn't work. Then we go to dipole induction. Well, there's no electronegative atoms, so there's not going to be a net dipole that we need to consider. Then we go to orbitals. All right, let's think about the negative charge here on the top. All right, so the negative charge, meaning that lone pair set, is going to be in what sort of orbital? sp3. All right, if we think about down here, where will those electrons be? Be sp2 or sp? Sp. All right, so now it gets a little bit abstract. Which one is longer as an orbital? sp3 or sp? sp3 is going to be longer. Why? Has more p orbital shape. We know p orbitals are longer, more oblong. So we could say sp3 is going to be longer. And over here it's going to be shorter because it has less p character. And then we can ask ourselves, all right, if you're a negative charge, meaning some electrons, would you prefer to be really, really far away from your nucleus, or would you like to have the nucleus close and nearby? Close, right? You think about the nucleus, it has a positive charge. Electrons, if possible, want to be close to that nucleus. So in this case, down here, this is actually more stable because electrons are held closer to the nucleus. that means that this must be more acidic. So it does get a little bit trickier, but typically the shorter orbitals stabilize that negative charge. Yep.
dq by the length of dq also by the strength the bonds?
The strength of what?
Bonds. It's like because they're like three bonds together.
Yeah, it's not related to strength so much as the orbital length. The orbital length is really the contributing factor here. Good question. All right. Now the thing that's going to really frustrate you is there are a lot of exceptions. This covers, I would say, 90% of the situations you will run into, but there are some exceptions. So I did want to show you some of them. All right, so the most common exception that you'll run into is this one, where we have ammonia. All right, ammonia has hydrogens, so we could think, all right, maybe this could give its hydrogen, or proton, I should say. And if we do that, what charge would this nitrogen have? It'd be negative. And we would create our conjugate acid. All right, let's compare that to acetylene down here, the one we just looked at. And I'll just draw it out again for clarity's sake. We could say, all right, it has a proton. And again, we can say, all right, we've got this conjugate base on top compared to this conjugate base on bottom. All right, let's work through the cardio rules. Charge, -1, tie. Then we go to atom. Are we looking at electronegativity or atomic size? Electronegativity, they're in the same row, nitrogen and carbon. So which one's going to be more stable with the negative charge according to the electronegativity trends? Nitrogen. So we would predict this. So we would expect this to be more stable due to electronegativity. It's actually not the case. Experimentally, when we do this, we would see that it's actually the reverse. This molecule down here is, I believe, about 10 orders of magnitude more acidic than the one on top. So in this case, orbitals actually override electronegativity. Students get really, really frustrated. And they will yell at me and they'll say, but you taught me these cardio guidelines, I spent a lot of time working on them, and now you're showing me an exception. As I'm sure you're all aware in chemistry, there are a lot of exceptions. The cardio guidelines are just that, they're guidelines. I won't ever put a problem on an exam or a quiz where I'm purposely trying to trick you. I will either give you PKA values or they will follow those cardio guidelines, but I want you to be aware there are outliers. Does that make sense? All right. I think what we'll do is we'll end there today. If you want to get started on your pod, you're welcome to hang out in the room for a few minutes. So.